Welcome to Chapter 22. This should feature some better sound quality because I now have a lapel mic based on Peter's recommendation, so thank you. So let's dive right in. You're going to see a lot of stuff here that looks very familiar to gravitation and the stuff that we learned in gravitation. So some basic definitions. Electric field, also known as electric intensity. You need to know the term in case it pops up on a test or something like that. It's the field created by an electric charge. Any electric charge will produce an electric field, just like we had any mass would produce a gravitational field. Test charge. We'll talk about test charges. A test charge, we think of it as a really tiny positive charge object that's brought into a field so we can test the strength of that electric field. Electric field lines, they are lines that follow the same direction as the direction of the electric field vector at any point around the charged object. And we're going to get into that more later. So, properties of electric fields. A small positive test charge is going to be pointing away from a positively charged object, but towards a negatively charged object. And so what that means is the electric field lines are going to point always away from positive and towards negative. And the electric field lines are continuous. None of them ever stop or cross. If you ever see an electric field drawing where the lines are crossing, then it's wrong. That never happens. And what we can do is when we draw them, we're going to have one electric field line represent a certain amount of charge. So we'll get to that. Electric field equations. You're familiar with this. The electric field is like the force per charge. You can think of it that way. Just like a gravitational field is the gravitational force per amount of mass that's there, this too is the electric charge, or the electric force per amount of charge. And so it's kq over r squared. And in the picture you can see it's 1 over 4 pi epsilon naught. 1 over 4 pi epsilon naught is the value of k. We're going to use k for now, but when we get to Gauss's law, we're going to be using the 1 over 4 pi epsilon naught because there are a lot of pi's floating around and in Gauss's law, so it'll be useful then. So basically, just like gravitation was gm over r squared, electric field, kq over r squared. Plain and simple. And we can think of it as electric field is the amount of force per charge. So E equals F over Q, where F is the electric field, the electric force. And the direction of the field is the same as the direction of the force. Right, so positive charges away from each other, positive and negative towards each other, and the units then are newtons per coulomb. Okay. So let's take a look. Recall this. This is the graph for the gravitational field due to a uniform solid sphere of radius r and mass m. And that's what, so we have gm r over r cubed for the inside, for the outside gm over r squared. Same thing is true now for the electric field near a charged object. However, you got to be careful, only for when the charge is distributed within. That would be an insulator. Only insulators will have an evenly distributed electric charge within the object. Conductors, the charge is always going to go to the outside. So this only counts for insulators. Where inside, it's kqr over r cubed, and outside, kq over r squared. Plain and simple, just like gravitational fields. Now, if we have a gravitational field for a shell, right, remember that, inside, g is 0. Outside, same as before, gm over r squared. Now, this is true for a spherical shell or a spherical conductor that's charged, has charge q on it. Inside, the electric field is 0. That's the same shell theorem that applies here, if the charge is distributed on the outside or if it's a shell. But then outside, same as before, kq over r squared. In this example, we've got test charge. So we start off A. We want to know the magnitude and direction of the electric field. and we want to know the force on an electron placed at the same location. All right, so we write E equals F over Q naught. We're just going to deal in magnitudes for now. And so this is 4 times 10 to the negative 4th newtons over 2 times 10 to the negative, what is that, 9th coulombs. And so we get 2 times 10 to the negative 5th newtons per coulomb. All right, so that's the electric field. And it's at 125 degrees, same as the force. For B, we're looking now at F equals QE. Same equation, we just rearrange it now. And the Q now is 1.6 times 10 to the negative 19th coulombs times 2 times 10 to the negative 5th newtons per coulomb. Look at how the units work out. The coulombs cancel. And we're left with 3.2 times 10 to the negative 14th newtons. And this would be at 305 degrees, or negative 55 degrees, because since this is negative, the direction is going to be opposite as before. So now drawing electric field lines, or in other words, lines of force. Here's an example, like if this is a positive charge, at this point, the strength of the field would be in the direction that's tangential to these lines. All right, and so now we can look at this. Notice none of the lines ever cross, and they're continuous. They just go on. The place where they would end would be at a negative charge, if they ended. So if each electric field line represented 1 microcoulomb, what is each charge? Well, you can count. 1, 2, 3, 4. If you go all the way around and you count all these, then there are 25 lines. That means each of these is positive 25 microcoulombs. Again, we can see that the electric field lines point in the positive direction, so away from the positive charge and towards the negative charge. Since these two are here, you can see that these lines start and end, start at the positive, end at the negative, and some of these go off the area that you can see, but if you count them up, you've got 13 here, 13 there, and 11 going kind of up and around and out, but then back in, 11. If these are the only two charges around, then all the electric field lines coming from this one will eventually hit this one. And in this one, so we're looking at the same drawing, but if each electric field line represents 5 microcoulombs, what's the charge on each body? Well, these are the same charge, so we get the same number of field lines coming from each. And we count these up, we get 24, so 24 times 5, so they're 120 microcoulombs. This one's positive, that one's negative. In this example, we can see that we have 4 microcoulombs, and then this one is negative 8 microcoulombs. That means, ultimately, this will have more field lines coming into it than this one has going out of it. So if we let each field line represent 1 microcoulomb, this one's going to have 4 coming out of it, this will have 8 coming into it. And they should be evenly distributed around the body. So for the 8, you can kind of maybe put points on this, like 1, 2, 8 of them around. I figure those are the lines that are going to be coming in. This one's going to have 4, so you have them evenly distributed around, top, bottom, left, right. The one on the right goes straight there. Top comes out and curves around. Bottom comes down and then curves around. And that constitutes these 3 here out of the 8. The others can be kind of curving, because we can think of them as curving around away from this positive charge. Same for these. This one will just go straight out that way, and then this one over on the right will come straight in from the right to the negative charge. So this is how you can draw electric field lines. And now for 22.4a, this is what you're filling in there. E is Q over, 1 over 4 pi epsilon naught, Q over r squared, or KQ over r squared. That's for magnitude. As far as direction goes, the electric field is the vector sum of all the electric fields of the charges around it. So if we have more than one electric charge, those add up as vector sums, the same way that gravitation did. And so let's take a look at an example of this, example 4. So now what we're asking is, what's the place where the electric field created by these two charges, 20 microcoulombs and 5 microcoulombs, both positive, is going to be 0. So it's going to be somewhere probably in here, right? The answer to part B, is there a region where it will always point, to the right? Over here. These are both positive. So these will always be, on this side, all electric field lines will always be pointing away. The answer to C, to the left, when x is less than 0, everything over here to the left will be an electric field pointing to the left. So now we have question A, where will it be equal to 0? So what we'll do is we'll set the magnitude of the electric field from the 5 microcoulomb charge equal to the electric field of the 20 microcoulomb charge. That's the place where they're going to balance out. Okay, so this is going to be kq of the 5 over r5 squared. And that's going to be kq of the 20 over r of the 20 squared. Right. Okay, so now where am I going to put this in here? Let's put it in here, and let's call this distance x. The distance from here to here, we'll make that x. Right. And then this is 0.1, right? So that means this distance is 0.1 minus x. So for this one, this is going to be kq5 over 0.1 minus x squared. And this is going to be kq20 over 0.1 squared. What's it? Or rather x. All right? X squared. Okay. So now we can kind of simplify some things. The k's cancel out. So let me come down over here now. This is going to be 5 over 0.1 minus x squared equals 20 over x squared. Cancel out and make this a 4. And then we can cross multiply. So we'll end up with x squared equals 0.4 minus, I need to multiply this thing out. We'll do this. 4.1 minus x squared. Then, put this under here again. So let's do x squared over 0.1 minus x squared equals 4. Now we'll take the square root of everything. End up with x over 0.1 minus x equals 2. And so here I'm going to have x equals 0.2 minus 2x, but I add that back over here. I end up with 3x equals 0.2. So x is going to be 0.2 over 3, which comes out to 0.067 meters. Right. So that means x is 0.067 meters. All right, so now let's take a look at example 5. This one's all in terms of Q and D and all that stuff. But it's set up kind of the same way. Here we've got plus 4Q, and here at coordinate D, we have negative Q. Right. Now where is the electric field going to be 0? It's going to be somewhere over here. Over here, the plus 4Q is going to overpower any electric field from this. So here, the electric field lines are always going to be pointing to the left. In here, all these electric field lines will be pointing from the positive to the negative. So only over here at some point is this larger charge going to overtake this smaller charge. Because think about it, from a very, very far distance, what does this look like? This looks like a plus 3Q charged object. And so we're going to be somewhere over here. So let's just put it here for now. and we'll call this distance x. That means this distance is d plus x. And we're going to do the same thing. The electric field from the positive is going to be equal to the electric field from the negative, right? So this is k 4q over, this is d plus x squared is equal to k q over, this is just x squared, right? This negative 1, that's just the distance x. For this one, that's the distance. Okay, so now the q's and the k's cancel out. And so I'm going to take this and put it up there. So 4 is d plus x squared over x squared. Now I'll take the square root of the whole thing. So 2 is d plus x, which is equal to x. So 2x equals d plus x. So x is equal to d. Right? Okay? And then that gives us the answer now to example 6. Because now example 6, notice that we've got 20 and negative 5. 20 is 4 times as much as 5, positive 20 and negative 5. So really example 6 is exactly the same as this, except that d equals 0.1, 4q is 20, and negative q is negative 5, all microcoulombs. And this is in meters. So now we already really have the answer to 6. The answer to 6 is that x is equal to this, since x is equal to d, when we have this situation. And like we said before, in the middle here, the electric field lines will always point to the right, and on the left over here, the electric field lines will always point to the left.